Okay, so Surendra, do you have any questions? Do you have any questions from the week's lectures? So Surendra and Nibeta, do you have questions? Or shall we move to today's class? Okay, so we'll move. Okay, so good evening, everyone. I'm Niketa. I'm a PhD student from IIT Madras, and I'll be covering some basic topics. So I'll be giving a brief of some selected topics from week 7 lectures, and then we will be solving some multiple choice questions. Okay. Okay, so last week we saw about activated sludge process, right? So, can you recount and tell me some brief introduction or whatever you understand about this activated sludge process? What happens during this? Any answers? So, in activated sludge process, we have a reactor in which we just one second, in which we suspend the microbes. Okay, the microbes are suspended, and then they will react with the organics present in the waste. Okay, and we also supply a lot of oxygen so that the microbes can live and they can respire and they can break down the organics present in wastewater. So, in this process, after this treatment, the water is taken, the wastewater is taken, and it is allowed to settle in a basin, in a sedimentation tank. So, after sedimentation, there will be some sludge remaining. Of course, the top layer of water is taken and it is sent to the next stage of treatment. But whatever sludge that is there, a part of it will be recycled. Okay, it will be sent back and it will be made to enter the feed tank. And this sludge, why we are recycling? Can you tell me the reason? why is it important to recycle the sludge, whatever is coming from this sedimentation tank? Why are we again putting it into the ASP? There should be some reason, right? It's okay if your answer is wrong.
And like, can you repeat the question?
Yeah, so I was asking, in activated sludge process, we have a tank in which the microbes are suspended. Okay, the bacteria is suspended and it is in contact with the organic matter. So this bacteria will break down the organic matter, and then it will be taken. The waste treated wastewater will be taken to the next stage, where it is allowed to settle in a basin. Okay, so that whatever sludge or solid particles are there, they can be collected at the bottom, and the remaining clear liquid at the top can be sent for the next stage of treatment. So, and then whatever sludge that we get at the bottom of the sedimentation tank is taken and it is reintroduced into the uh, activated sludge process tank itself, the treatment tank. So, I'm asking, can you tell me one reason why it is done?
Allowed to again for any tertiary treatment or something like that.
No, actually, for I mean, again, this some of the sludge will be taken for treatment anyway. Okay, most of it actually, most of it will be taken for sludge treatment. A part of it will be recycled. So the reason why we do this is so that the sludge, right? It is rich in bacteria, right? So whatever sludge that we get at the bottom is rich in bacteria, and that is why we introduce this back to the treatment tank, so that the bacteria can disperse fully, so that we can maintain adequate bacterial concentration in the uh, ASP tank. So that is why we are doing this recycling.
Which means like you're telling that the sludge will be again introduced so that again it will get recycled, like from the first.
Yeah, yeah, that will happen. See, some quantity of sludge will always remain in this loop.
Okay, so that some quantity is from the leftover sludge that again goes back into the ASP.
No, you are, I mean, it need not be the same sludge, because recycled sludge also has the possibility of going to the treatment. Okay.
Okay.
But
So
the same
no, you said
quantity.
ma'am, the water after it goes, there will be a few sludge which is remaining, and that will again go with the bacteria.
No, no, no. I think you misheard me. What I said was, this is the treatment tank, okay?
Yes, ma'am.
Yeah. And here we do the settling.
Yes, ma'am.
So, what happens in a settling tank? Whatever treated wastewater comes, we just allow it to settle for some time, so that whatever solids and sludge are there, they will get sedimented and settled at the bottom. Okay. So, this is sludge. So, this sludge will, most of it will be taken for treatment. Okay. But a part of it, maybe 10-20%, will be taken for recycling.
Okay, ma'am.
And
Now
why?
I understood.
Yeah. So we do this recycling to introduce the bacteria in the treatment tank, so that sufficient quantity of bacteria is maintained.
Okay, ma'am.
Okay. So if this is clear, then we can move to the next one, which is the model. Model is basically a mathematical equation to depict a process. So in order to depict this process, we have an equation which is something like this. So the rate of inflow of microbes in the system minus the rate of outflow of the microbes in the system plus the net rate of cell growth in the tank. This should be equal to 0. Did you understand this? So what we are saying here is the rate of inflow of microbes, whatever microbes are coming at the inlet, minus the rate of microbes which are flowing out of the system, mainly as sludge. Now at the inlet, we have to consider both the microbes that are present in the inlet feed wastewater also, plus whatever recycling that recycled sludge that we are putting inside the tank. Okay, so this will include both the inlet wastewater as well as the recycled sludge. So both of them will constitute the rate of inflow of microbes in the system, minus the rate of outflow of microbes in the system, minus whatever we are taking out of the system in the form of sludge, plus the net rate of growth in the tank. Obviously, when the wastewater comes inside the tank, the quantity of microbes is going to be less. After a while, the microbes will start to multiply and their population will increase. So the rate of inflow minus the rate of outflow plus the rate of net cell, the rate of their growth is going to be 0. Is this clear?
Yes, ma'am. Actually, in today's session, you will be discussing the. You'll be discussing the week 8 things, or generally what will be done, ma'am? Because I'm new to this.
Okay, so what I usually do is I'll give a brief about whatever some selected topics from the week's lectures, and at the end of the session, I'll be making you solve some MCQ problems.
Okay, ma'am. For the final exam, ma'am, should we like how should we prepare? Like, should we prepare like the JE? Like, since I'm no like, should I just watch those lectures and prepare from them, or lectures and assignment is enough, or like how should I prepare for the final exam, ma'am?
Yeah, attending live sessions, watching lectures, and solving assignments should be more than enough.
Because the final exam will also be like the assignment one.
That I'm not sure.
No, for the numericals, is the tutorial thing enough?
Yeah, I think it should be. The assignments cover pretty much whatever was discussed in the lectures. So if
Yeah,
you
ma'am.
prepare accordingly, I think it should be fine.
When I see the lecture and I do the assignment, I find some things easy, but there are few sums that the numerical part is somewhat confusing, because the sums that they discuss in the class and the thing that is asking the assignment is a bit different.
Yeah, that will be there. So you have to practice similar problems.
Okay, ma'am. So this will be okay, ma'am. You continue. Thank you.
So there will be some reference textbooks, right? Maybe you can read those.
Yeah, yes, ma'am.
Yeah, but usually whatever is covered in the class and live sessions and assignments should be more than enough.
Yeah, then it's okay, because we are doing this side by side, so we won't have time to do the whole books and all.
Yeah. So this can be represented using terms like this Q into XO, where Q is the rate of inflow. So rate of wastewater inflow is denoted by Q, and XO is the concentration of microbes in the inlet. Okay. So this minus now here the term QW refers to the waste, the sludge that is taken for treatment and disposal. Okay, so that is represented by QW. and Xe is the amount of the concentration of the microbes in that is coming out of the effluent. So you can understand this better using this diagram. So this is the tank where the treatment is happening. Then you have the settling tank here. Now the wastewater is coming from the treatment tank to the settling tank, and from the settling tank the effluent is coming out. So the microbial concentration in the effluent is Xe. Okay, and whatever sludge we are going to recycle, so that is denoted by this. At the inlet, you have the flow rate as Q, and S naught is the concentration of organics present in the inlet. So this is the influent stream, and QW is the amount of quantity which is going to be recycled. I'm sorry if I mentioned it otherwise. So QW is going to be the quantity which is recycled, and Q minus QW is the quantity that is going to be wasted. Okay, and the organics that are coming along with it is going to be denoted as Se. So the effluent concentration, the concentration of organics in the effluent is denoted as Se, and Q minus QW is the flow rate of the effluent. So this is getting recycled here, and so the volume of the tank is denoted by V, and X is the concentration of microbes in the tank. C is the organics that are present, and this is the settling tank, and this is the aeration tank. So this is sludge recycling that we are doing.
Ma'am, what is that Xe, ma'am?
Yeah, Xe is the concept. Yeah, I'll write all those terms now.
Okay, ma'am.
QW is the flow rate of the microbes to be wasted. So X naught is the inlet concentration of the microbes. Xe is the microbial concentration in the effluent. XR is the microbes concentration in the waste sludge. So now I think we can relate to this equation. So Q is the inlet flow rate, and that multiplied by X naught, which is the inlet concentration of the microbes. That minus Q minus QW into Xe, which means whatever outlet is there. This is actually the equation for microbial concentrations. Sorry, microbial mass actually. So the mass in the inlet minus this term denotes the mass that is going out through the outlet, and this will be the mass that is getting recycled. So whatever is coming in the inlet minus whatever is getting taken to the effluent plus whatever is getting recycled plus the rate of growth. Is going to be equal to 0. Is this clear? Okay, so I'll explain again. So this is an equation where we depict the mass of microbes in the system. So in the inlet, we have the microbial mass equal to the flow rate into the concentration. So flow rate is what? Meter cube per second, right? Multiplied into concentration is given in terms of say mass per unit volume. So I'm assuming that it's in milligrams per meter cube. Okay, so this will give you in terms of mass per second. Okay, considering that we'll just ignore the time term and we'll consider that this is happening for a day. So this equation will give us the mass of microbes that are passing through and out of the system in a day. Okay, so this will be the inlet mass. Inlet equals to how much of inlet minus whatever is coming out plus the rate of growth is going to be equal to 0. Is this clear?
Yes, ma'am.
Okay, so shall we move to the next topic? Or do you have any questions? If you have any questions, let me know.
Ma'am, that RG, what is it, ma'am?
Yeah, this is the rate of growth.
Okay, ma'am. Okay, ma'am.
So I've represented in terms of RG. So this is the rate of growth multiplied by the volume of the tank. So this will give us the mass of microbes that are growing inside the tank. So when we take at any given time, the mass that is coming in the inlet minus the mass that is coming in the outlet and the mass which is going in the for recycling plus whatever by microbial growth is there inside the system. This all this should be when they are together, it should be equal to 0.
Yes, ma'am.
So the net rate of microbial inlet is going to be the rate of outlet plus the rate of microbial growth. So the rate of growth of microbes is given by this equation. Where y is the yield coefficient. This is mass of volatile suspended solids or VSS divided by mass of BOD removed. And RSU is the ratio of mass of cell that is grown to the substrate utilized. So this is basically how much of bacterial mass has grown. Okay, say maybe 1 grams or 2 grams. That mass divided by how much of organics it has used up to achieve that growth. For example, it has grown by maybe 100 grams. So in order to grow by 100 grams, it will need some amount of organic waste in order to digest and grow, right? So that is the substrate. So this denotes the organics in the waste. So when we rearrange this equation and we assume that x naught equals to 0, that means the initial microbial concentration is going to be 0, then we get this term q by v into y by x into s naught minus se equals q minus qw into xe. Now kd here and here, they denote the rate of microbial death. Now if we take theta, or better known as retention time. So retention time is the time which we allow the reaction to happen in the aeration tank. The time for which the liquid is retained in that tank is called the retention time. So that is given by volume of the tank divided by the flow rate of wastewater. So this retention time will have a critical value. So this critical value is necessary because if we let the wastewater be in the tank for a short time, which is, for example, theta c is maybe 2 days, and we let the liquid remain in the tank for maybe half a day or just 1 day, then the microbial population will not grow. Okay, so in order to maintain sufficient microbial mass, we have to let the retention time cross the critical retention time. Okay, so this critical retention time is given as V into X by Q minus QW into XC plus QW into XR. Now taking 1 by theta, we have y by x into s naught minus se. We are just substituting all this in this equation. So this is 1 by theta c plus kd. So this will give us y into kse by ks plus se equals 1 by theta c plus kd. If we solve this, then we will get S equals to As into 1 plus Kd into theta c by theta c into Yk minus Kd minus 1. So here K is the maximum substrate utilization rate. Which is given as mu max by y. Now mu max here is the maximum specific growth rate. And Ks here is the substrate concentration. At specific growth rate. Now the specific growth rate value for this finding out Ks is going to be mu max by 2. So exactly when the substrate specific growth rate is going to be maximum substrate, when you have the maximum specific growth rate divided by 2, which is the peak value, we take that and we divide it by 2, and the corresponding substrate utilization rate is going to be the substrate concentration at the specific group. It's going to be called Ks. So usually there will be a plot Ks and mu max. So at mu max by 2, whatever, so it's going to, sorry, it's not something like this. So this is going to be a shaped curve. So at mu max by 2, whatever substrate, this is going to be K. So at mu max by 2, whatever value of K is there, so that is going to be called Ks. Now, x theta by S naught minus S is going to be yeah. So now we'll come to the loading criteria. Which is substrate loading per unit biomass. Which is given as, which is also known as food to microbe ratio. So this is given as Q into S naught by B into X. So if we neglect SE, then 1 by theta C is going to be Y into F by M minus KD. So this means that 1 by theta C is going, 1 by theta C is inversely proportional to F by M ratio. Or in other words, theta C is inversely proportional to F by M ratio. So what this means is the critical time which is required for microbial growth is inversely proportional to the food to microbe ratio. Okay. So if we increase the food and we reduce the microbial population, then it means that your theta C is going to be high. Sorry, theta C is going to be low. Okay, moving on. So, like I said earlier, in order to make sure the microbes are degrading the organic compounds, we have to supply enough oxygen. So, when we are designing this treatment plant, we have to account for how much oxygen is required. So, we have to calculate that beforehand. So, the oxygen requirement is given in terms of this equation. So the oxygen requirement is the mass of oxygen required per day this is going to be equal to mass of ultimate BOD that is removed minus 1.42 times the total active mass of organics that are wasted per day. So here the organics that are wasted per day will refer to the bacteria which is coming out and removed as sludge. So this is nothing but the sludge. So the oxygen required is amount of BOD ultimate that is removed minus 1.42 times the mass of organics that are wasted. So the difference between the BOD that is removed minus the organics that is wasted will give you how much microbes have grown. So in accordingly you have to supply the oxygen. If you know how much microbes are growing per day, so accordingly you will supply the oxygen. So that is what we are calculating here in this equation. And the observed yield, which is y observed, which is y by 1 plus theta c into kb. Now this is given as the mass of MLSS or mixed liquor suspended solids. In kg. So this is also known as MLSS divided by the BOD5 that is removed. This is also in kg. So the next step is figuring out how to supply the oxygen or how to get the air supply system. So conventionally, the aeration and mixing will be uniform throughout the tank. So we will have aerators here at every point, and from the top we will have mixers. So mixing and aeration will be done uniformly. But there are some issues with this method. It's that when wastewater is entering the tank, that is when most of aeration is required. When it leaves the tank, we don't need lot of aeration. So that is why uniform mixing will not be that efficient, because you will be supplying more air, and for supplying air you need a lot of electricity. So for using this air supply and mixing equipment you need a lot of electricity. So if you are providing both aeration and mixing at certain places in the aeration tank where it is not required, then that is a waste, right? So this is not energy efficient, and that is why they have come up with many other designs. So the second way is tapered aeration. So in this, the aeration is intensified at the inlet. And it is reduced towards outlet. So this method will prevent CO2 wastage. Sorry, O2 wastage. and it is more energy efficient. So here by efficiency we mean how much of um, BOD is getting removed to how much of spending is done or how much of energy is used up to run this. So when we compare the conventional method with the tapered aeration method, we find that in tapered aeration we are reducing energy losses, and that is why the system becomes more efficient. Okay. The next one is step aeration. So here in step aeration, what happens is we introduce a new feed at every point. So maybe one inlet will be here, second inlet will be here, third inlet will be here. So what happens is when we provide something like when we provide multiple inlets, so the first at the first inlet we have only one. So this will get aerated and mixed, and by the time we come to the second inlet, the first portion is already having treated water. So we only require aeration and mixing for one particular stream. Okay. And in this system, we also make sure that the the wastewater is leaving from both sides. And this will ensure that the oxygen supply is uniform. Then other method is supplying just oxygen without air. So what happens? So air will have only 21% oxygen, right? So if you provide air also 100% air, so in that only 21% is going to be utilized for microbial growth. But instead, if you provide 100% oxygen, then microbial growth is going to be very fast. So there will be a high microbial activity or high bacterial activity. And your sludge volume is going to be reduced because most of the organics will be digested, and therefore you will have very less sludge. And you will also have higher settlability because your sludge is going to be very dense. So because of that, your settling settling characteristics will improve. So in conventional technique, only 5 to 10% of oxygen is utilized. So in but when we supply 100% oxygen, we ensure that 90% of oxygen is utilized. Do you have any questions?
No, ma'am.
So next, coming to the next important topic, which is sludge volume index. So sludge volume index is also denoted as SVI. So this is the volume of sludge.
Ma'am?
Yeah. The sludge volume index is also denoted as SVI. So this is the volume of sludge that. Do you have any questions? Yeah.
No,
Do you
ma'am.
have any questions?
No, ma'am. There is a little bit connection disturbance in between, ma'am. I can't hear you completely. Means flow at a flow.
Oh, okay. So I was just talking about sludge volume index.
Okay.
So sludge volume index is the volume of sludge that is settled after 30 minutes. So what happens is, to measure this, we will take an apparatus known as an Imhoff cone. So it's basically a cone-shaped apparatus, and we will put the wastewater containing sludge in it, and we will allow it to settle for 30 minutes. So after 30 minutes, all the sludge will be settled at the bottom. So the volume will be measured, and that volume is called the sludge volume after settling for 30 minutes. So that is going to be the numerator. So this sludge volume is given in terms of milliliter of sludge that is settled per liter of wastewater. Okay. So this divided by the microbial concentration. So MLSS is nothing but the concentration of bacteria. So this is going to be the concentration of the bacteria in the sludge. So if we take the ratio of these two, it should be ideally sludge volume index should be ranging from 40 to 100. Okay. So your concentration of bacteria in the sludge should be slightly higher than the sludge volume. So as to ensure that you have to get a lower sludge volume. But what happens if you have a higher sludge volume? Meaning that your sludge volume is high, but the concentration of the bacteria in that sludge is very low. What that means is you have a lot of organics, and the presence of organics in the sludge will indicate that your treatment process has not been done properly. So the bacteria has incompletely degraded. So this will happen when there is a condition called sludge bulking. So this will happen when the sludge volume index is greater than 200. So this ratio is supposed to be divided by 1000. So when you do that, you will get a. I mean, if when you after you calculate this, your number comes out to be more than 200, then it means the sludge quality is very poor. And there is something called sludge bulking which is going on. That is why your sludge volume index is very high. So this is caused by a certain type of bacteria called filamentous bacteria. Now, filamentous bacteria will not be very helpful in degrading organics, and it will have a very low density, so it won't settle. What happens if something doesn't settle easily? Obviously, your volume is going to increase. When you have something which is highly dense and settled, it's going to come at the bottom. When you have something which is lightweight, it keeps on floating, and therefore your volume, that is volume of sludge, is going to look like it's high. So this is caused by the presence of filamentous bacteria. Okay. So now we have seen ASP. Then we will come to trickling filter. So this is the second most commonly used aerobic process after ASP. So what happens here is you will have a filter like apparatus. So on this we will have various particles, okay? Like maybe Rashid ring. Are you from chemical background?
No, ma'am. I'm an masters in environmental science student, ma'am.
Oh, okay. So rashig ring will mean some particles which are like this, cylindrical, basically like this. Okay. So this type of particles are there. So they will be arranged like this. I'm just, for the sake of drawing, I'm just making it very distant, but actually they'll be packed together. And over this, when you pour wastewater, you can have many ways by which you can do that. You can have some sprinklers on both sides. So the sprinklers will sprinkle wastewater here. So when this happens, the wastewater will come and it will trickle through, or it will pass through and it will go to the next layer. From this layer, it will come to this layer, and finally it will come out. So this thing is called trickling. So when we supply raw wastewater at the top, so whatever rashig rings or whatever particles are there, they, because of the bacteria present in the inlet raw wastewater, they will grow a layer of bacteria. Okay, so imagine this is the surface of the rashig ring. Over this, a layer of bacteria or slime will grow. Okay. So over time, as we pass more and more wastewater, the layer will be thick. It will start forming a thick layer. So the height of this layer will increase. Okay. And sometimes it can be as thick as 2 mm. And when we have a very thick layer, what happens? This part that is near the media, so this portion does not have any contact with air. So this portion is going to turn anaerobic. And the top portion is going to be in contact with air, so there is going to be gas exchange. So this portion is going to be aerobic. Okay. So what happens when anaerobic conditions develop? Aerobic bacteria is going to die. So when the slime layer becomes very thick, then what happens is the aerobic bacteria at the bottom, they will die. And what happens is the slime layer will get easily detached. So when you have a very thick slime layer, slowly it will get detached and it will fall down. So this process of falling down is will be instigated even more by the water that is coming from the top. So if the wastewater is coming at a certain speed, then that is going to instigate this process of waste moving down. The slime layer passing down and falling down. So this process of the slime layer falling down is called sloughing. This is initiated by the flow of wastewater over the trickling filter. Now, one problem with trickling filters is that there will be a lot of flies. So, fly nuisance is there. Because unlike in ASP, we don't have a tank where we are suspending the media. Instead, we are keeping the media stationary and we are spraying the water from the top. So there's a high chance that fly will come and sit on the filter. It will lay eggs and those eggs will multiply. And there will be a lot of flies related issue in this. So this cannot be seen in advanced ASPs because we are supplying oxygen and we are aerating it continuously, and the media the bacteria is suspended there. So the performance of the ASP is given by this equation, SE by SI equals to exponential of minus K to LA to A by Q. So where SE is the concentration of the settled effluent from the filter. So this is given as milligrams per liter, and SI is the concentration of the influent to the filter. This is the empirical rate constant. And A is the filter cross-sectional area. So here, AS, this is the specific surface area, which is area per unit volume. Okay, and Q here is the wastewater flow rate. And M and N are constants. And L is the filter depth. So this is the depth or the height of the filter. Next, coming to upflow anaerobic sludge blanket. It is also known as USB in short. So here the wastewater will flow from bottom to top. So this is completely aerobic. The gases generated are collected and taken out. So it is completely sealed. So the wastewater will enter from the bottom, and once it enters, it will flow through this blanket, which is basically made of sludge. Okay, so it will flow through this blanket, and in this blanket there will be anaerobic bacteria which will act on the organics and degrade them. And whatever it will, as if it, I mean, once it flows through, also this reaction will happen. So this is the point where the bacteria will come in contact with the raw wastewater, and further when the raw wastewater moves up, here the reaction will take place. And after the reaction, whatever sludge is forming, it will come down and it will thicken the layer of this blanket. So the blanket will become thicker and thicker. Okay. And after degradation, whatever gases are formed, usually in anaerobic processes, we will have carbon dioxide, methane, H2S, etc. So whatever gases are produced, they will be taken out through this outlet, which is situated at the top, and they will be taken out. Then we have lagoons. So can you tell me, lagoons are aerobic process or anaerobic process?
A lagoon is like an artificial pond, ma'am. Am I correct?
Yeah.
I think it is an anaerobic process.
Why do you feel like that?
Ma'am, no, ma'am, no idea, ma'am.
Okay, you are partially correct and partially wrong. So lagoons are like this.
Okay, ma'am.
The water will come in, and the top layer is going to be aerobic because there is going to be, this is exposed to air. So there will be gas exchange, and that's why this layer is completely aerobic. But after the wastewater comes, and here it will react with algae and bacteria. So after the reaction happens, the sludge will settle at the bottom, And here at the bottom, the oxygen supply is going to be less. So that is why there is going to be anaerobic conditions created at the bottom. And further, when we add more and more sludge to the top, so it is going to make a densely packed layer which does not allow any exchange of gases. So that is going to create the anaerobic condition here. So here the main drivers of degradation in lagoons is algae and bacteria. So algae will supply oxygen, which will be taken up by the bacteria, and the bacteria will in turn give CO2 after degrading the waste. So that will be taken up by the algae for its own growth. So like this, the cycle will be repeating, and both algae and bacteria will be coexisting. So there are some design considerations here. So first we have to consider how much BOD needs to be removed, and what are going to be the how do you want to be the effluent quality. So and then the effect of temperature. Why temperature is important? It's because temperature affects the rate of dissolution of gases. So that is why we have to mind the temperature of the process also, and how much oxygen is required. And how much energy is required for mixing. Sometimes why we consider energy for mixing is sometimes we will provide some aerators, so which will aerate the system. So that's why we are considering this energy for mixing also. And after a point, if the sludge layer keeps on rising, sludge keeps on building, then it won't be good for the algae and bacteria growth. So that is why from time to time we have to remove the sludge. So that comes under the solid separation. So the equation for lagoons is given as S by S naught 1 plus K into volume by flow rate. So this is 1 by 1 plus K into theta. So here S by S naught, this is called the fraction of soluble BOD that is remaining. So S here is the BOD that is in the tank, and S naught is the inlet BOD. So S by S naught will give you the fraction of the soluble BOD that is remaining. Now by BOD I am referring to the organics that need to be treated. K here is the rate constant. Theta is the hydraulic retention time. A is the reactor volume. And Q is the flow rate. Now if we have two ponds in series, then the equation is going to be 2 or more. So here it's basically the same equation, but we have one factor called N. So n is the number of ponds. If you have 2 ponds, then n is going to be 2. You can just substitute 2 in this equation and you can calculate. So, can you tell me some drawbacks or disadvantages of activated sludge process?
Addition of oxygen is more.
Okay.
Ma'am?
Yeah, but like let's not compare between aerobic and anaerobic. In aerobic processes itself, we have
Ma'am,
techniques
am
like
I audible?
yeah, you are audible.
Ma'am, am I audible?
So additional oxygen is required. Yeah, that is correct. So even in trickling filters, we provide oxygen. So when compared to those methods, why do you feel you have any other reasons? Can you hear me? So is my slide visible now?
Ma'am?
Can you hear me? Is my slide visible now?
Yes, ma'am.
So let's continue with this.
Okay, so let's
So we were
continue
discussing
with
about
this.
the drawbacks of ASP.
So we were discussing about the drawbacks of ASP. So
One major drawback
Yes, ma'am. We need
one major drawback is
yeah.
yeah,
a more amount of oxygen.
more oxygen. Not really. So we even have trickling filters. Even trickling filters require aeration, and even rotating biological contactors require aeration. So why? It's like not just in terms of aeration, even in terms of area.
Okay, ma'am.
So when you look at ASP, the tanks are huge. We need two tanks that do, one for settling and one for the reaction to take place. So there are two tanks. The first one is the aeration tank where the reaction happens, and then we have the settling tank or the sedimentation tank.
or the sedimentation tank.
So the area required naturally
So
because we have two
the
tanks. So
area
the area
required
required for
naturally
them is
because
going
we
to be
have
higher.
two tanks, so
Whereas in a
the
trickling
area
filter, you
required for
just
them is
have
going to be
one
higher.
filter
Whereas in a
which is
trickling
shaped like
filter,
a
you
tree.
just have one
So whatever
filter which is shaped like a
this
tree. So whatever
particular area is
this
what is required.
I mean,
And
this
similarly
particular
for
area is what is required. And similarly for
biological contactor, it's going to be
rotating
one
biological
tank.
contactor, it's going to
So
be
this is
one
going to
tank.
be like a wheel
So
here.
this is going to be like a wheel here. So this is going to keep
So
rotating.
this, I mean, all
So
these
this,
are
I mean,
processes which
all these
require
are
lesser area.
processes which require lesser area.
But
But
in order to
in order
combine
to
less
combine
area
less
with the
area
same
with the same
efficiency as
efficiency as advanced
aerated sludge
aerated
process,
sludge process,
we
we
I mean
I
we
mean
can
we can
use
use
sequential
sequential
batch
batch
reactors.
reactors.
So
So
this
this
will
will
combine
combine
all the
all the
steps of
steps of
ASP.
ASP. So in ASP, what do? You just add the water, add wastewater, and then you allow it to react. You
You
also
also
aerate
aerate
it,
it,
and
and
after
after
the
the
reaction
reaction
is
is
over,
over,
you will
you will
allow it
allow
to
it to
settle
settle
down
down
in a
in a
settling
settling
tank.
tank.
So
So
these
these
are
are
the
the
various
various
processes
processes
that
that
are
are
happening
happening
in
in
the
the
ASP
ASP
tank.
tank.
So
So
in
in
one
one
tank,
tank,
if
if
you
you
want to
want to
do
do
all
all
these
these
processes,
processes,
then
then
you
you
have to
have to
do
do
it
it
as a
as a
sequence,
sequence,
right?
right?
So
So
first,
first
we
we
have to
have to
do
do
equalization,
equalization, and then we have to do aeration,
and then we have to do aeration,
and then
and then
clarification or settling
clarification or
in the
settling in the
settling tank.
settling tank.
So if we
So
were
if
to
we
use
were to
only
use
one
only
particular
one
tank
particular
for all
tank
these
for all these
processes, then there
processes,
has
then
to be
there
some
has to be some
sequence.
sequence.
So
So
first we
first
will
we
add
will
the
add the
wastewater and
wastewater and
equalize it.
equalize it.
After some
After
time
some
we
time
will
we will
aerate it.
aerate it.
So
So equalization
equalization
we'll do it
first.
first.
After
After
some
some
time
time in the
we
same tank we will
supply
supply
oxygen
oxygen
and
and
we
we
will
will
do
do
aeration.
aeration.
And
And
after
after the reaction is complete, in the
same
same
tank
tank we will allow
allow it
it
to
to
settle
settle
so
so
that
that
the
the
sludge
sludge
is
is
settled
settled
at
at
the
the
bottom,
bottom,
and
and
the
the remaining
remaining
liquid
liquid
will
will
be
be taken
taken
to
to
the
the
next
next
process.
process. So the sludge will also be removed in the same tank. So the advantage of this process is that it is space saving, because instead of two tanks we are doing everything in a single tank. Um,
It's
it's
just that
just
you
that you
need
need
sufficient time.
sufficient time.
So
So
in an
in an
ASP process, the aeration will happen simultaneously, reaction will also happen simultaneously. But here in this sequential batch reactor, we have to first equalize, and that will take some time. After that, we have to do aeration, that will take some time. And then we have to do clarification, which will take its own time. So here, instead of space, the time is divided. Instead of space. So instead of having two reactors for aeration and settling, we are combining in the same reactor but at different times. So first we will do aeration, after that we will do settling. Okay, so basically there are 4 types of operations that are taking place in an sequential batch reactor. The first one is the fill. So in this one, whatever wastewater we have, that will be filled inside the reactor. So the reaction, there is no process happening as such. Only the tank will be filled with wastewater. Okay, so that will take some time. There is no mixing or aeration. Just influent will be entering the tank. Okay, so then the next step is mixed fill. Or just mixing. So now the tank is totally, it is filled. Now we will do mixing. And here in this stage there is no aeration, just mixing. And anoxic conditions will develop. So can you tell me what is anoxic? Any answers?
Less availability of oxygen or no oxygen.
Sorry?
There will be no oxygen.
Yeah, there will be no oxygen. Also, there won't be any. Instead, like in anaerobic conditions, also instead of oxygen, some other maybe nitrates will be used for oxidation process. But here there is no oxidation happening, so that is why it is called anoxic. Now this will be useful for denitrification. And then we have the next process, which is aerated fill. So in this step, we will be aerating the liquid. So we will give some aerators. Oxygen will be supplied. So here mixing will also happen as well as aeration. So we can, in this stage, we can create both aerobic and both oxic and anoxic conditions. So that can be done by switching on and off the aerators. So oxic conditions will be required for nitrification, and anoxic for denitrification. So accordingly, we can switch off and on the reactor. So the next step is the react phase. So the fill phase had three types. Static fill. So this is where no mixing or aeration takes place. So this is also called static fill. In mixed fill, along with filling, we will do mixing, and in the aerated fill, we will do mixing plus aeration when the fluid is entering. So the next step is the react phase. So in this one, there is no influent entry. The influent entry is completely stopped. Mixing and aeration will take place. So the difference between aerated fill and react is that here simultaneously influent is coming and we are also doing mixing and aeration. But here the influent entry is completely stopped and it is only mixing. So this will ensure a higher efficiency because as soon as the fluid enters, it is allowed to mix and react. So here the mixing and aeration will take place. And then the third step is called the settle. So here the sludge is allowed to settle at the bottom. So there will be no mixing or aeration, no movement at all. Only the sludge will be allowed to settle, and even the influent is not allowed to enter, so it is completely closed. And then the last phase, which is decant. So in this phase, the whatever supernatant is there after settling, so this supernatant will be allowed to flow outside and it will be removed. So the last phase is the idle phase. So here there is no process happening, no inflow, no mixing, no aeration. And no settling. Okay. So the duration of one cycle will be approximately it will be 4 to 6 hours. And the time taken for each cycle is given as a sum of time to fill plus time to react plus time to settle plus time to decant and the time for idling. So idle phase is generally used when we have some cleaning work or there is some repair work. So at the end of each cycle, we have to do idle. We have to keep the tank idle also. So when it comes to nitrogen removal in an SBR, so in an activated sludge process, nitrogen removal is not possible because we are only maintaining aerobic conditions. And for nitrification, for denitrification, we need anaerobic conditions. So where there is no oxygen. For denitrification, we need anoxic conditions, and for phosphate removal, we need anaerobic conditions. So these cannot be possible in an ASP or an aeration tank. So that is why we are using SBR, so that we can combine both carbonaceous BOD removal with denitrification and phosphorus removal. So all of this can be done in the same reactor. So that is why we are using a sequential batch reactor. So the first step for nitrogen removal is nitrification. So in nitrification, ammonia nitrogen will be converted to nitrate and nitrate. So this will take place in aerobic conditions. And the second step is denitrification. So here anoxic conditions will be maintained, so there won't be any oxygen. So in anoxic conditions, what happens is the bacteria will use nitrate as a source of oxygen. I mean, from nitrate it will using nitrate it will oxidize the organics. So instead of oxygen, the electron acceptor here is nitrate or nitrite. So instead of oxygen, nitrite or nitrate will be getting reduced, and it will form. I mean, the bacteria will, the organics will be getting oxidized. And in this process, the nitrogen gas is released. So, in order to summarize both nitrification and denitrification, so we can write something like this: the ammonia nitrogen is converted to nitrite, and then nitrate. And again, during denitrification, this nitrate becomes the electron acceptor, and it will reduce to form nitrite. And further, it will become nitrous oxide, and finally, nitrogen gas. So, can you tell me the advantages of sequential batch reactor? We just discussed all of them now.
Both aerobic and anaerobic can be performed, ma'am, like phosphate, which needs an anaerobic condition.
Yeah, that's right. So, this will nitrogen removal can happen. Area requirement is less. So the flexible operation is there. So if you want, you can have anoxic conditions, aerobic conditions, anaerobic conditions. So all this can be controlled. So there is some flexibility in the operation. And the initial cost of setting up the process and the equipment is less because only one tank is there. So we do not need a lot of funds to run the process and setting up the treatment plant. And the power requirement is also low. At the same time, there are many limitations or disadvantages of SBR. So it is highly sophisticated, meaning that you need to time all your processes. So if your fill process is going to take 20 minutes, then you have to give 20 minutes. So if you and similarly, if you take some 30 minutes for decantation, then you have to give 30 minutes. If you even spend one more minute on decantation, then the next batch of wastewater, it will come in and you won't have time for decanting. So since that sophistication is required, so that level of expertise is required to maintain the correct flow of operations. So this becomes highly sophisticated, and you also need proper machinery and tools to ensure that the flow is smooth and there is no delay or lag. So this is going to be highly sophisticated. And then it requires high maintenance also. because like if something gets repaired, then you have to immediately fix it. If some equipment is getting damaged, then it requires immediate attention, because even if one process is getting delayed, the other processes will stop, and that will create a huge problem. So unlike in an ASP, unlike an ASP, here we don't have that much like we don't have a lot of we cannot waste any time in this process. So we have to make sure that things are running very smoothly. So that is why it requires a high maintenance also. Okay, so then we will come to granular ASP. So can you tell me why it is called granular ASP? What do we mean by granular here? What is granular?
Granules is being used, ma'am.
Yeah, what granules?
No idea, ma'am.
Okay, so here what happens is, so generally in an activated sludge process, when we settle this after the aeration process, we will allow the wastewater to settle, and it will form a layer at the bottom in the settling tank, which is called sludge, right? So if we give so if we give enough time for the sludge, enough aeration has been given, then the sludge tends to become dense. Now, what do we mean by sludges becoming dense? It is getting more and more solid, and the volume is less. So, obviously, when there is less volume, then the mass is going to increase. So instead of regular sludge, which is going to be very liquidy and very having a high volume, we are going to get a dense and compact sludge, which requires very less volume. So this will save a lot of time. I'll tell you why. And also the cost. So when you have a highly dense biomass, which is densely packed, it is going to have many layers inside. Okay. So the topmost layer is going to be what? Can you tell me what is going to be the topmost layer? Is it going to be anaerobic, anoxic, aerobic? Because it is open and it is going to interact with air.
Aerobic.
Yeah. Obviously. So the top layer is going to be aerobic because there is going to be oxygen in the air and there is going to be gas exchange happening on the surface. So obviously the outermost layer is going to be aerobic. Now, what happens in an aerobic condition? Your BOD will be removed, mostly carbonaceous. And nitrification will happen. Okay? Nitrification is where we just discussed it. So nitrification is where ammoniacal nitrogen is getting converted to nitrites and nitrates. So when you have a densely packed sludge, the topmost layer is going to be aerobic. The second innermost layer is going to be what?
Anoxic.
Yeah. So this is going to be anoxic. There is no oxygen. So therefore denitrification can take place. And the innermost layer is going to be anaerobic. So in the innermost layer, we are going to have processes like phosphorus removal, which requires anaerobic conditions. So instead of having regular sludge, which is like a huge mass of watery substance. Instead of that, we are going to have granules of sludge, which is also made of the same bacteria, but it is densely packed, and that is why the innermost layer will not have any oxygen. The outer layer will have a lot of interaction with the air, and that is going to be aerobic. So the advantage of having granular sludge is that I told you it is going to save cost and time. So why is that? It's because all the three processes are happening in the same granule. So unlike in a regular sludge, which is used only for aerobic processes, so in a granular sludge, we can have both aerobic, anaerobic, and anoxic conditions simultaneously. So all three processes can happen simultaneously. So it's going to save you a lot of time. And how do these granules form? So first there will be cell-cell interaction. So where one cell will interact with the other cell, and they will move down together. So they will come very close to each other, and then they will form an aggregate. So many cells together will form an aggregate. And when all these cells are together, what they release some polymer. Usually cells will have a polymer called extracellular polymerase. What happens is so it is this extracellular polymerase which ensures that the bacteria lives and moves in water. So it provides a kind of protection barrier for the cell. So when these cells are aggregated together, all of them will together release this extracellular polymer. Okay. So this polymer will tend to bind even more cells together. So it's acting like a binding agent. So ultimately you have some dense flocks, okay, dense granules of these bacteria. So inside there will be many cells. Okay, so this is how the granules are formed, and finally the granules will be shaped. So after some time there will be intense aggregation. So there will be the pressure itself will many granules together will form next to each other. So the pressure from the external forces will itself make sure the granules are shaped. Okay. So then we will see something brief about phytoremediation. So can you tell me what is phytoremediation?
Removal of pollutants with the help of plants.
Yeah, with the help of living plants. Very good. Very good. So in this, if we have any organics, like if we supply just domestic sewage, the plant is going to utilize that organic waste, and it is going to grow with the help of the organic waste. So the organic waste will first be broken down, and it will be uptaken. Whereas if you have some metals, these metals cannot be broken down and they cannot be digested by the plant. So they are just going to absorb these metals and they are going to act as a filter. So if you have a site which is contaminated with, let's say, some toxic metal like mercury, so you have some plants which can absorb the mercury. So through the roots, it will tend to absorb the mercury and it will trap it inside the stem or the leaves, etc. And it will continue to grow. So as a result of that, whatever mercury was there, the amount of mercury in the soil will get reduced. So over time, when you plant many such species here, so it is going to ensure the remediation of the site. Okay, so then after the plants trap the metals, then they will be harvested. They will be cut, and they will be harvested and removed. So this can be used for on-site removal instead of taking the contaminated soil and then treating it and putting it back. We can just grow some plants on the same site so that in the same place the plants will grow and they will just remove all the metals. So here we will have two important terms, which is bioconcentration factor, which we have discussed in the earlier classes, and then we have the translocation factor. So translocation factor, this is given by the ion concentration in the stems or leaves. Which is given as in terms of micrograms per gram. So the concentration of ions in the stems or leaves, so whatever mercury or heavy metals you have, the concentration of those mercury in the leaves or the stems. So here the concentration of the metal is given in terms of microgram, and the mass of the metal is given in terms of microgram, and the mass of the stem or the leaves are given in terms of grams. So this will be divided by the initial ion concentration in the roots. Initial ion concentration in the solution. Roots. So again, this will also be given in terms of micrograms per grams. So why we are using the translocation factor is to tell how much of the metal is traveling from the root upwards into the stem and leaves. So if the translocation factor is high, it means that the concentration of the metal or ion is higher on the stems and leaves when compared to the roots, which is a good thing, because if you have more concentration of metals in the roots, when we cut the plant, the root is what is going to be inside the soil, right? So the contamination is not completely removed. Then we will go for phycoremediation. So phycoremediation is removal using bacteria or microalgae. Micro or macroalgae. So the algae will be grown in photobioreactors, which are basically reactors which are, which will be in contact with light. So you will have a light source. So and there will be one medium where the algae will be grown. So since algae growth is dependent on light, so we will have different types of photobioreactors of different designs. According to your needs, you can adjust and you can design those reactors. Okay, so we have come to the end of this session. We will move on to the question and answers now. So if you have any questions, let me know. Any doubts?
No.
Okay, so we'll start with.
In the lagoon also we will be using algae, no?
Yeah, but in lagoon it's a combination, right? It's a combination of bacteria and algae.
Okay.
Yeah. And moreover, it's a natural system. It's not an artificial one.
Okay.
So it's like you have a pond or a lagoon, and yeah, lagoons can be artificial also. But what I mean to say is, it's not like a reactor. It's not made of concrete. It's just a place where there is water and there is algae and bacteria, and sunlight is being used, right? Sunlight is there, so bacteria will use only the algae and bacteria will use only natural resources. Whereas when you come for phycoremediation, it is artificial. Artificial light source will be provided, artificial nutrients will be given for the algae to grow. So this is similar, but it is artificial and that one is natural. Okay, so going to the first question. Can you see my slide?
Yes, ma'am. Yes, ma'am.
So can you tell me what is the efficiency of the extended aeration process?
80 to 90%.
Not really. So what is extended aeration? In regular aeration, we are supplying just oxygen and we are mixing it and then we are done with it. But in extended aeration, we are providing aeration for a longer time than what we usually provide in an aerated sludge process. So here, since the oxygen concentration is more, the bacterial activity is also going to increase. So this will mean that bacterial microbial growth is going to be high. So that means the removal efficiency is going to be higher. So the correct answer is 90 to 95%. And also it is going to ensure that the organic loading is low. Okay, next question. Which of the following can be done to prevent sludge bulking? So can you remember what is sludge bulking? It is caused by what? So we discussed about filamentous bacteria, right?
Yes, ma'am. Provide sufficient aeration.
Yeah. So when we have sufficient aeration, so growth of filamentous bacteria is suppressed. So phosphorus removal will occur in which of the following conditions? Can you see my slides?
Yes, ma'am. Yes, ma'am. It's anaerobic.
Yeah, correct. So we just discussed here. So aerobic will remove CBOD and nitrification. So anaerobic is useful for removing phosphorus. And ancic is useful for removing, for denitrification. So facultative means both aerobic and anaerobic. Like for example in lagoons.
Can we say trickling filter as an facultative, ma'am?
Trickling filter.
No, actually,
because
anaerobic conditions are
developed,
developed,
but that means that the aerobic bacteria is going to die, and because of that, immediately the sloughing will happen. So the slime layer will be completely removed. Whereas when you have a lagoon, the anaerobic conditions and aerobic conditions will coexist.
So this portion will
So
be
this portion will be anaerobic,
Okay, ma'am.
and the top portion
and the top portion is going to be aerobic.
So these conditions
So these conditions will be maintained throughout.
Okay. Whereas
Okay.
in a trickling
Whereas
filter,
in a trickling filter, it will take time for the aerobic condition to develop, and immediately after some time, immediately the sloughing will happen, and the slime layer will be completely removed.
Okay, ma'am.
Okay, so the facultative
Okay, so the facultative conditions are not going to coexist for a long time.
Next question. What is the ideal COD to N ratio for sludge
Next question.
granulation?
What is the ideal COD to N ratio for sludge granulation?
No idea, ma'am.
Okay, so the ideal rate is going to be 2 to 5.
Okay, so the ideal rate is going
at 2 to 5. The growth of heterotrophs is going to be less.
Ma'am, I can't hear you.
at 2 to 5. The growth of heterotrophs is going to
At this ratio between 2 to 5, the
at this ratio between 2 to 5, the rate of heterotroph growth is
because most of the bacteria are autotrophs. Whatever we are using for activated sludge process is going to be
Ma'am, voice is not audible.
autotroph. And if heterotrophs are there, then they are going to consume the autotrophs and their population is going to reduce. So that's why for the formation of granulated sludge, this 2 to 5 COD to N ratio should be maintained so that the growth of heterotrophs is reduced. Okay, last question.
Okay, last question. Which of the following plants can be used for removing chromium and lead?
Ma'am, sunflower?
No.
No idea, ma'am.
Okay, so the correct answer,
Okay, so the correct answer is Indian mustard. So it can remove both chromium and lead from water. Okay, so if there are no questions, then we will end the session. Do you have questions?
No, ma'am.
Okay, then thanks for joining. We'll meet in the next class.
Thank you, ma'am.